Okay, so let's start. Welcome everybody in this new session of the CIMNE seminar course. Today we have with us Dr. Kees, who is going to talk us about fluid structure interaction problems solved with grain resolving and volume-based computational models. And he comes from the US Army Engineering Research Development Center, if I'm not mistaken. I'm sure that this topic will be very interesting for most of us who are also working in similar topics. So, please.
Great. Thank you. So thanks again for having me. It's a great honor to be here. So this is work with a lot of collaborators and team members, and so I tried to highlight several of them in particular. So Agalos Dimakopoulos and Giovanni Cazzuto are at HR Wallingford Laboratory in the UK. It's a laboratory that's very similar to ours. I believe you in Spain have IH Cantabria, is that right? Is that it's a major hydraulics and coastal laboratory. So we have similar goals, and so we've been collaborating on the development of these new models. And then, of course, Manuel Quesada de Luna, who's here with me today, is a postdoc in our program, and Yong Yang, who's back at our lab. And then Milad Raksha is a mechanical engineering graduate student who did an internship with us last summer and just made a lot of progress on coupling of some of the discrete grain resolving models that I'll show. So first, why are we doing this, particularly from our laboratory? So the U.S. Army Corps of Engineers is responsible for inland navigation, so all the commercial navigable waterways. It's also responsible for inland flood control and flood protection projects, and also for some ports and coastal storm surge defenses. And in all of these areas, sediment plays a major role as it is driven by hydraulics. So one example here is the Bluestone Dam, which was originally designed for 430,000 cubic feet per second, but it now needs to be updated to handle a much larger flow. So these types of redesign projects are something that the Corps of Engineers is faced with a lot. And one of the issues that you have in something like this, where you have a much higher flow rate passing through it, is that you have the potential for scour downstream of the concrete infrastructure. So if you get scouring of the sediment, sorry, that's kind of entertaining, but you can get undermining of the foundation because you get scour underneath the concrete structure. So scour is a major problem, but predicting it is very difficult. There are, as we'll talk about a little bit, there are good riverine models for looking at sediment transport in 2 dimensions over large scales, but once you're dealing with a very 3-dimensional problem, the evolution of that scour is more difficult to model, obviously, in 2D, so you really need to resolve the 3-dimensionality of it. So that's one of the motivations. Another area where we deal with things like sediment, although in some cases the grains can be quite large, but we're still essentially dealing with fluids and waves interacting with granular structures, is with breakwaters. This is a refueling platform in the Azores, and so it has a large breakwater out in front of it to protect it from storm waves like that one. And these storms have enough energy to rearrange the armoring of the breakwater, these large concrete armoring blocks. And I imagine you guys have seen this as well, because you have these types of problems out on the northwest coast of Spain, where you have these huge waves. So again, it's an area where fluid structure interaction is important, but particularly with these types of rubble and granular type structures. A last example that I found very interesting is, and just was learning a little bit about recently, is what's called the Old River control structure on the Mississippi River. So you can't read, I'm sure, the titles here, but basically before the European settlement of the continent of North America, the Mississippi and the what is now the Atchafalaya Basin ran parallel to one another. And then the natural meandering processes of the river, I believe it's in the 15th century, caused a large oxbow or meandering curve of the Mississippi to actually intersect part of the Atchafalaya Basin. But the flow at that time was so slow on this fork of the Atchafalaya that the Mississippi went back to its normal channel. So everything was okay there. At some point, an engineer decided that this was taking too much time, and there was already an old channel here, so they basically cut a new channel to orphan this oxbow so the steamboats could go straight down the river there. And then, of course, over the long time, that had some unintended consequences. So the first thing it did was it cut off the upper part of the old oxbow. But then, at certain times of the year, flows started going down the Atchafalaya in addition to the Mississippi. And so the risk that the Mississippi would actually completely change its course and flow down the Atchafalaya, bypassing New Orleans and going into a different place in southwest Louisiana, became a real risk. And so the Corps of Engineers built some large, expensive infrastructure here, which you can see from the aerial view here. It includes spillways, dams, it includes a hydroelectric power generation facility. But around this facility, sediment issues are very important. So the Mississippi River, of course, carries a lot of sediment. There are reasons why you might want to divert some of that sediment down the Atchafalaya, but at the same time, you want to protect against this rerouting the entire Mississippi down the Atchafalaya. So again, interesting near field or near structure hydraulics interactions with sediments that are important here that we'd like to understand. So the goals of our research project at ERDIC at the moment are to try to understand this process at two scales. So we want to use microscale models where we're resolving individual grain motion and contact inside of a containing fluid or two fluids. So there's a kind of a simple simulation where we have an array of rigid spheres or cylinders that we then release into the flow and they settle to the bottom. But of course that's not feasible to do for the types of scales where we'd like to do hydraulic engineering. So we want to use these microscale models in sort of our standard multi-scale modeling approach to derive constitutive relations for volume average models. So in this case, I'm just showing a similar issue where I've got a diffuse granular material that I then allow to settle into the bed. And so we're trying to work at both scales. Of course, from the computational side, a lot of the tools are similar. We need fast Navier-Stokes solvers that are robust and accurate. And we need to deal with multiple phases. So we can share a lot of the infrastructure between these two scales. So to go into a little bit of how we formulate the different models, I use this simplified cartoon. So we have fixed domain boundaries. These would be the exterior of the square here. Then we have internal moving phase boundaries. So we have an air-water boundary that we care about. That's what we're going to use to model our water waves and various other kinds of things happening at the free surface of between the air and the water. And then we have solid boundaries. And both of those are moving relative to the fixed domain boundaries. And so there's no simple change of coordinates that allows us to get away with the fact that we have moving interfaces. And we also have topological changes. We can get bubbles, droplets forming with the water, and then we can also have solids that are coming into contact, and in the long run we might have solids that are breaking up. And so we have topological change that we have to deal with as well. So our main modeling assumptions are that all phases are incompressible. That could be relaxed, but it simplifies a lot of our work. The solid phase is just going to be a collection of rigid particles, and we won't consider any interphase mass transfer. So there's no dissolution of solid phase into the fluid phase, or no dissolving of air into the water phase. Then at the microscale, that is where we're actually resolving the solid particles, we assume that each point is occupied by exactly one phase. Once we do a volume averaging approach, then of course the solid phase and the fluid phase are going to be represented as a mixture, and so there will be a variable volume fraction of the solid phase for the macro scale model. And I'll talk about that in the second half of the talk, that formulation. So one of our core tools that we use is the level set method. So I'll briefly give you some of the details on that. We partition the domain omega into the air, water, and solid domains. And then we define the air-water interface as the zero level set of a scalar function phi. So it's defined as phi equals 0 on the air-water boundary, gamma AW. Then we extend phi away from gamma using the convention that it'd be a sign distance function. So our convention is that if it's negative, you're in the water phase. If it's positive, you're in the air phase. And then the value of that scalar function is the distance to the interface. And so that's enforced by this equation 2, which is the iconal equation. We also describe the solid particles in the same way. And then there's some tricks that you can do with level sets. For example, if you want to get the entire solid phase domain, you can take the minimum of all the individual level sets for each solid particle. And then we define things like material properties using the characteristic function of the level set. So if we take the heaviside, the scalar heaviside function of the sign distance function, then we get the characteristic function of a set. And that's how we shift between things like densities and viscosities as we go between different phases. So again, these are kind of classical at this point, well described in books by Osher and Sethian in their early papers. So the governing equations for this model, we start with incompressible flow in each phase. And then for the solid phase, we're just going to have 6 degrees of freedom motion, so a system of ODEs for the solid phase particles that includes potentially interaction terms. So we're solving the evolution equation for each particle and then potentially also interaction forces when they collide or roll past each other. We may also include a surface tension jump. So the boundary conditions between the phases would be continuity of the velocity and either continuity of the pressure or a jump in the pressure due to surface tension. So this is really the heart of one point of my talk that I came here in part to discuss with Santiago. We've been using an Immersive Foundry method to enforce the no-slip condition at the solid grain. So at the surface of each grain, we assume continuity of the velocities. And so we need to actually enforce a no-slip condition, which is really that U equals US at the boundary between the fluid and the solid. And the way that we've been doing that, for the most part, is we take our equation for our Navier-Stokes equations, which gives us continuity and a momentum balance, and then we do a boundary integral for our solid surface grains where we represent the no-slip condition, but we enforce that boundary condition using the Nietzsche method. So we have, instead of just a simple boundary integral, we have terms that look like the flux term and the momentum that would arise by integrating the stress by parts, and then we have what's called an adjoint term, or adjoint consistency term, and a penalty term that arise from the Nietzsche method. The thing that we don't do that many immersed and embedded methods use is that we don't do boundary integration. Instead, we use another trick from the level set community where we convert a boundary integral to a volume integral by multiplying by the Dirac delta function. In this case, it's the smoothed Dirac delta function of the sign distance field. And so this gives us weak imposition of the no-slip condition at the solid phase. And the reason we started doing this initially was that we didn't want to try to, if you were going to enforce these boundary conditions using boundary integrals, you would actually have to subdivide some of your cells and a cut cell type approach. And we were trying to avoid that and specifically avoid assumptions about the actual representation of the interface that we were using. So if we wanted to use quadratic level set methods or cubic level set methods, then the cut cell problem there is somewhat more complicated than just intersecting a plane with a cube or a plane with a tetrahedron. And so this way, we were somewhat released from that constraint. We could use higher order methods for the level set representation. So the other things that are interesting maybe about this formulation is that we also enforce inside the solid phase. So I mentioned earlier that we can evaluate this characteristic function that this would be 1 in the solid phase and 0 in the fluid phase. So If it's 0, I'm in the fluid phase, I have the usual terms in the Navier-Stokes equations. If it's 1, I'm in the solid phase, those terms are gone, and I have just this penalty term within the solid phase. So within the solid phase, there's a penalty which is similar to many other types of models for multi-phase flows like this. So there's a method by Gawinski that uses a Lagrange multiplier approach, and it ends up using a penalty like this. And so I know this is one of those kind of, I guess, maybe dirty tricks that you find a lot of people are actually doing this in order to represent moving solids. It's just putting a penalty in the solid phase. The difference here is that we do have kind of formal consistency through this Nietzsche type enforcement of the boundary condition, and that also gives us a precise way to evaluate our lift and our drag by calculating the boundary intervals that are appropriate to get the lift and the drag on the immersed boundary. So that's what we put a lot of our time into. We have also been experimenting with something called the shifted boundary method that was recently produced by Scavazzi and Main. I won't go into detail about it, but the basic idea of that approach, whereas currently we're using a smooth Dirac function to evaluate the boundary integral along this curved surface that cuts through a cell. Scavazzi and Main's method extrapolates the slip condition at that boundary to one of the existing cell boundaries. And so it doesn't require that you deal with cut cells because of the way that it extrapolates out to a different boundary. There are other more sophisticated methods, the cut fin method, and then the method by Santiago and Verdugo and Martin that look very interesting that we'd like to look at in the future. Any questions so far?
When you say Happy Double was here 2 weeks ago, so
okay, so everybody's got that too, all right. So there are some additional considerations from a practical point of view that I think, I guess, I know you guys have not overlooked, but the fact is when you use any type of unfitted or cut cell representation, you're not really, there's no free lunch. You're not suddenly able to represent an interface by some really large cell that is cut by the interface. You're still going to need to do some type of refinement near the interface to get accurate computations of fundamental quantities like drag and lift. And so you do require, in some sense, a smearing of the interface, and if you want that smearing to be not have a large physical effect, then you need to do refinement around the interface. Just while I'm at it, I'll mention a couple other things that we're working on to try to improve our accuracy. So we are working on higher order level set schemes and new schemes for conservation. So Manuel has a nice paper in progress on a new conservative level set scheme that's a monolithic scheme. We're also looking at the cubic extension of the shifted boundary method. Also interested in looking at adaptive quadrature and other types of ways to evaluate these cut cell boundary integrals accurately. We've also been in the process of shifting our stabilization schemes from in Navier-Stokes equations from variational multi-scale methods or SUPG methods to intra-viscosity type stabilization schemes. And we're also working on scalable preconditioning. The preconditioning work is in the vein of sure complement methods for the Navier-Stokes equations, if you're familiar with some of those classical approaches for using a block decomposition of the Navier-Stokes operator. And there will also hopefully be a paper on that coming out soon. And then some related projects on pod methods for model reduction and H and R adaptivity in the dynamic setting that we're in. So, what do we have? So this is a simple example just of two spheres in the grain resolving approach. So you can see the spheres contact the walls and they come into contact with one another. So that's, and this is fairly robust in terms of intergranular contacts and things like that. So that was our main goal, and that's mostly met by all the methods that we've looked at in terms of robustness. We can also do, I don't have a nice video, but we have, in this case, I've shown in black here the air-water free surface, so we can drop particles from the air phase into the water phase and that sort of thing. We can also add surface tension. I don't have that. There's one piece missing to representing surface tension in the particle case. We have good representation of the surface tension itself, in this case for a bubbly flow, but what we're lacking is the boundary conditions for the air-water interface as it intersects the solid phase. And there we need to do some additional work at looking at the dynamics of the contact line motion that we use in these models. So certainly if you have experience in that area, I'd love to talk to you because it's an area that is still, I've not seen a lot of work in that area. So in terms of convergence tests, here's a simple Stokes problem where we're going to apply the no-slip condition at a strip through the center of the boundary, of the domain, and to represent that as an immersed boundary. Here we show the IBM results. This is our simple immersed boundary method using the smooth delta functions. So you can see the air is converging, but the rate is first order or possibly worse. But and then we yeah. So this is yeah, the different components of the velocity u and v. And then we look at SPM, and we get closer to second order, which is nice. So it's clearly the extra effort of doing handling your cut cells more carefully seems to pay off in terms of asymptotic accuracy for that simple problem. So next we move on to some classic tests. One falling disk. So I'm not going to run the whole simulation. I'll skip on, but this is this has been studied by a number of authors. So we want to look at its equilibrium position as it makes its way down the domain and other types of dynamics. So our results are here. So the center of the domain is roughly 2, and then these are some of the other results. So we're doing okay. And this is using the immersed boundary method, not the shifted boundary method. Horizontal velocities, similar. This is just the fall velocity, so we're getting reasonably good prediction of the fall velocity. However, when we were looking at these problems, we started to see a lot of noise in the calculation of the drag and the lift, and so we went back to some of the standard CFD test problems for simple geometry. So there's Schaefer and Turek, of course, have developed a long time ago now, so that's some nice benchmarks that are well known. And so we went back and recalculated those with the immersed boundary method. And you see here, again, we have to actually do quite a bit of refinement near the solid surface that wouldn't be necessary, at least not as necessary with a fitted boundary method. So we're paying a price for our immersed boundary method. And so this is the comparison of the two. There's really, at this point, if we do sufficient refinement, to the eyeball, you get the same types of vortex shedding properties and the same types of boundary layers. If you look at the drag and the lift coefficients, here we're doing a comparison of what we get from the shifted boundary method and from the immersed boundary method. The value for a conforming method and most of the published results are in they're right around 3, a little bit above 3, so they're closer to our IBM results. And the phasing is a little bit off on the vortex shedding. But these things, the phases of the vortex shedding are, of course, very sensitive to the mesh, and so that's a little bit to be expected. So, but clearly we have some work to do. We may have a bug in our SPM method, but there's still some sensitivity to these different approaches that we don't quite understand. Also, pressure drops are relatively accurate, but some small differences. We also looked at sedimentation of 2 particles. This is call this the kissing, drafting, and tumbling problem. So in this case, the second particle is drafting behind the first particle, so it's able to actually catch up with it and they come into contact. And then you get the drafting and tumbling as it nears the bottom of the domain. So this is paper. Both of these were studied heavily in the paper by Lewinsky on Lagrange multiplier approach. Yeah. Like I said, our results here are qualitatively relatively good. They seem to be matching some of the other results that are out there. We did have some issues with the rotations of our particles being a little bit off, so we're still investigating that. Yeah, so these are looking at general trends in comparison of y coordinates of the two particles, x coordinates of the two particles, horizontal velocity. So anyway, that's kind of where things stand right now with our discrete grain resolving method. Is we're still working on validation, and we're also working heavily on scalability. I think the largest problem that Lewinsky did was about 500 particles. I know that people nowadays can do into the thousands of particles, and so we are not there yet. We're trying to work out some of the details of our scaling issues. Now moving on to the macroscopic models. So the idea here is to take either our microscale model or microscale data and then to pass it through some type of filter. So classic filtering approaches are time averaging, like you would do with Reynolds average Navier-Stokes, or volume averaging, as you do with porous media, or in some cases you do both. In this case, most likely you would do some type of a space-time average. But if you're lucky enough to have a filter that works, you get these nice filtering properties, and that allows you to come up with this new set of equations for averages at the large scale. So if I look at just just look at the mass conservation for one of the phases alpha. So I would have my mass conservation statement would be d rho alpha dt plus div dot rho alpha u alpha at the microscale. And so I multiply that by the characteristic function, and now I average over all of space with my filter. And doing that, I end up, and I guess employing generalized functions, we end up with a mass conservation statement at the larger scale. And now my new variable is the volume fraction theta, and a filtered or average velocity u alpha. You do the same thing for the momentum, and you get a momentum equation. One of the nice things about these tools is that you end up with this more or less the same form that you started with at the smaller scale, just with the extra need that you come up with some closures that represent some of the averaging processes. So in this case, when we go from the small scale to the large scale, we end up with new source and sink terms, which are the transfer of momentum between the fluid phase to the solid phase, and vice versa, and also between air and water phase. So that, if we're just thinking for simplicity about water and solid particles, then these are effectively the upscaling of the drag and the lift. So they're the averaged contributions of drag. So momentum lost from the fluid phase into the solid phase, and then the matching term in the other direction. Yeah. So in this slightly simplified form, I get the interface terms needing closure, and you also would get the need to come up with a new macroscale viscosity or stress tensor. So just to quickly talk about some of the closure considerations. First of all, there's no guarantee that it's solvable. And of course, there are many areas where people have solved for decades to find closure relations and not necessarily succeeded. There are lots of tricky things that can occur in the upscaling process. One thing that can happen is that your closure relations at the large scale, if you do it in an ad hoc way, they may actually violate basic thermodynamic principles, and so you need to actually try to constrain your closure relations to other considerations like thermodynamics. So in our particular case, one of the nice things is that there's been a lot of work done in industry history on closures for particulate flows. And so part of our work is really to determine how applicable those are to natural sedimentary processes. One other nice thing about our whole approach here is that because we're using level set methods at the micro scale, it's relatively simple to actually compute the fields of the averages that are needed at the large scale to do our own microscale numerical experiments and upscaling from our microscale model. So what do these terms look like? As I mentioned, the interface momentum transfer term, which would be the source sink terms from fluid to solid, they look like a drag term. So they're multiplied by the sediment fraction, some constant beta, which is actually a function of, not really a constant, I guess, it's a function of the velocity and the sediment fraction. But it's just penalizing the difference between the fluid phase and the solid phase. There are some other terms that arise due to the averaging process, which also go into the interface momentum term. And these are more or less pieced together by different researchers who've looked at different regimes. And so you can see that there's actually a jump in one of the coefficients as I've changed the regime that I'm in based on the particle Reynolds number. So that's just kind of an example of the complexity of the interface momentum terms that would go into that. Because, I mean, that's complicated enough, I'm not going to spend time to go through the stress closure relations, but the stress tensor itself is no longer just a constant viscosity times deformation rate tensor. It's, again, a complicated gadget that looks at different flow regimes and things like that. So I think there's a lot of work to be done here in understanding the stress. So at the macro scale, to quickly discuss some of the numerical methods that we're using. So we're using phase continuity, equation 23. There we're using variational multiscale stabilization for that approach. We're using P1 finite elements. Just recently we added the entropy viscosity schemes for that. So we're also using a projection scheme based on relatively recent work by Vermond and Salgado for the multi-phase momentum system that we produce. And so far, those aspects of the scheme seem to be working well. So here's a simple example. We start with a strip of sediment at uniform concentration, and it falls more or less at a constant velocity. So not a very exciting problem, but it is one for which we have some data. And so this is a comparison. So Soulsby is a researcher who was at H.R. Wallingford for many years, who did a lot of work on experimental data and came up with some nice correlations for the fall velocity as a function of the grain diameter. Or I guess these are non-dimensional, so there's density in there as well. But anyway, we're getting reasonably close results for the fall velocity at different concentrations. And these are, of course, relatively low concentrations where we get this behavior. So here's a problem that we just did recently, so it needs more work. I would end with this because I find it very interesting. This is a strip of sediment the density is quite high here. So it's a very dense strip of sediment, and it's in a tank with air and water. And on the left-hand side, I have the velocity, and on the right-hand side, I have the sediment concentration. And so what we see here, as opposed to in the lower concentration strip problem, is that we have definite formation of an unstable interface and a fingering type instability here. So we have work to do on this. The thing that we have just added most recently is really on the numerical side, and that is Manuela added a special mass mass conservative sediment volume fraction limiter. One of the issues that we kept having with these complicated closure relations is that, of course, our numerical models don't necessarily, they don't adhere to the physical constraints of the problem, and so we really need to place emphasis on numerical schemes that have discrete maximum and minimum principles like the physics do, and so the volume fraction limiter is needed in order to prevent. In this case, the volume fraction is limited to be under 0.75. And while the constitutive relations in an ideal world are constructed in such a way that the volume fraction doesn't violate that, your numerical method, it won't necessarily do that, and so you'll get overshoot. So in conclusion, these tools are in an open source software package called Proteus, which is our in-house toolkit for investigating finite methods and developing models. I know you guys have a great toolkit in-house here as well. A couple of things about that is we're trying to maintain a boundary between the physics, the constitutive relations and model formulations, and the numerics. That way we can allow researchers in numerical methods to hopefully come to relatively complicated physics and model setups and apply their new numerical techniques on real-world problems. It's parallel, it's unstructured. We do have some higher-order methods. There's kind of a decade worth of investigations in various things that are stored away in it. We did release it under the MIT license, so it's one of the first tools in our laboratory to be made officially open source. So we're proud of that. And then it includes these pretty specialized hybrid level set volume fluid tools that I've mentioned several times that are in there. One of the main places where we've done a lot of work. Lastly, I'll mention just a few things that we're working on that you might be interested in. So the three-phase RANs I've just discussed. We're also working on two-dimensional wave models, so an extension of the Green-Nogni model for dispersive waves. We have a shallow water equation solver that Manuel implemented and that is in a paper that will be coming out soon. And then, some work on the shear complement conditioning that I've already mentioned. The current release is 1.5.1 and it's available on GitHub, so I'd love it if you would take a look and use it if it's useful to you. And I have references here, and I'll be happy to give you this talk if you're interested in any of the things that I've talked about. Thank you.
Thank you very much. So I think we have time for a few questions. Any of you want to start?
At one point you mentioned that you were imposing artificial limiters because you needed that since the discretization of the problem was taking you to values that were not physical. But I'm not sure that even the continuous model has those limits in it anyway. Does it?
So, not in general. So again, I skipped over the math here on the stress closure, but this model that we're looking at does have mechanisms in it that drive the velocities to zero as you approach a critical volume fraction. And so formally, I doubt anybody's ever proved that there's a discrete maximum principle in there, but there is a mechanism to prevent, basically as you approach the critical volume fraction, the solid phase is becoming a solid. So the stress tensor is actually shifting from that of a viscous fluid to something more like an elastic solid. So there are mechanisms in there that are trying to, prevent exceeding a critical volume fraction. But certainly our numerical methods don't enforce that. And there are many very useful models of sediments that I've only recently started looking at that don't even attempt to do that. They simply use, for example, they'll use a mixture of Navier-Stokes equations and transport equations and just give a settling velocity. And so in that case, certainly there's a physical limit to it, but the equations themselves would not have any mechanism.
The problem is that the mechanisms that give you the limit in reality are of a different kind completely to the ones that you're trying to describe here, because these limits come when particles start to touch each other, and that is
That's right.
a different regime.
Yeah. These sediment, the stress closure relations in here do have intergranular contact, an upscaling of intergranular contacts in them.
Yeah, but sometimes it's a normalistic regime when they are bouncing off each other. But when they start to get into a packing configuration, sometimes that's another regime altogether. You know? Even if you have contact, you don't have this packing limit.
Yeah, I see. Yeah, that's a good point.
Any other questions? I have one question, or a couple of questions. You talked about, you got some results with the immersed boundary method and with the shifted boundary method. I guess that you usually work with the immersed boundary method, you use the shifted boundary method just for comparison, or do you usually also use the shifted boundary method?
So we have not been using the shifted boundary method for discrete particle simulations. And that's partly because we're trying to work out some of the issues with the variations in the drag and the lift. So, you know, one way of looking at this in terms of FSI is as a partition scheme. You do a step where you calculate the fluid flows, you integrate the stresses, you get drags, and then you do you take a step with a system of differential equations. And that's very sensitive to the drag forces that you calculate. And so my gut feeling is that the immersive boundary method, even though the one that we're using is clearly lower order, that may actually be helping stabilize the partitioned FSI simulation in that case, because it's less sensitive to the motion of the boundary. It smears it out a little bit, and so you get more stable computations of drag and lift.
So that's why you're using it.
Yeah, but we'd like to get the SPM method working and look at some of the other approaches, obviously. It would give us the provable higher order accuracy.
And then you also, well, you started with distinguishing like between the microscale models and the macroscale models. And so in your opinion, that you used both models, which is the way that you will use them in the end? I mean, will you try to combine them at the end to solve larger problems, or which is the aim of or the goal at the end of the day? So to work with the macroscale models and get information from the microscale, or what is your objective in that sense?
Well, in the short term, I think our laboratory has a lot of applications for both. Like we do a lot of physical experiments that have small numbers of particles that we're studying in a flume, and in that case, doing a grain resolving computational model to augment that would be very useful. But certainly at the scale of doing engineering for redesign of a hydraulic structure, you can't afford to do that, certainly not for sands or something like that. So that I think at the engineering scale, you're going to need the volume average models eventually, but there's still a lot of utility to the grain scale model. And then, and of course, the holy grail, I guess, of this is to have a really functional multi-scale analysis tool, so that you don't necessarily have to go out and parameterize your constitutive relations for the volume average models. If we can get a sample and then we can simulate that numerically, then we can do the closure virtually.
But that's still work to do, right?
That's a long way off.
Okay, thank you. Are there any other questions? If not, let's dive in.
Just one last question. When you upscale the models, when you go from a microscale to the macro scale, do you apply volume average? Because
yes,
you could apply other types of average. But
the models that we're looking at right now are doubly averaged. So they're volume averaged first, and then they're time averaged. So there's some of the...
But do you use averages in time, like with time start before that moment, or all around the moment?
It'd be like a window.
A window.
Yeah. So, I mean, I think of the time averaging coming in the same sense that you do time averaging when you're dealing with a turbulent flow. That at the end of the day, you can't resolve the temporal dynamics in a practical manner much better than you could manage the spatial variations at the microscale, so you end up averaging over both. So I don't have the references in my talk slides here, but Vladimir Nikora, I think, in the UK has done a lot on doubly averaged flows like this for both moving beds and also just for fixed beds where this is important. Thank you.
Are there any other questions? Okay, so let's thank Chris again.